All right, so now we're going to define angular momentum, which is pretty easy to define and might be obvious if you've been paying attention. L, which is little l in this case, is our angular momentum of a particle, which is r cross p of the particle, radius cross the linear momentum of the particle. So like torque is radius cross uh, force of the particle, angular momentum is radius cross momentum of the particle. So dl dt is equals dr cross dt cross p plus r cross db dot dt by the product rule, which is just v cross m cross v plus r cross dp dt. V cross mv is going to be equal to 0 because r v times v sine of 0 degrees is equal to 0. So it just becomes r cross dB dt, which is equal to torque. So dl dt, in the same way that dp dt, the change in linear momentum is equal to force net, the change in angular momentum is equal to the net torque. So, uh, what about a rotating body, about body of a bunch of different particles put together? So for this, we take Li, which is the particle, a singular particle, and say that Li is Ri times delta Mi, where delta Mi is just the tiny piece of mass that is being counted. I don't know why we can't just say that this is mi instead of delta mi, but it's just a convention that the book uses, so I'm going to use it too. Times vi sine 90 degrees, because uh, the radius, if you're going around in a circle, or if your particle is spinning around like something like uh, this, or this isn't a very good example because it's hard to tell what's going on, but something like this. Oh, that was silly. Then the velocity of the particle is always going to be perpendicular to the radius, as you can see in this diagram on the bottom right-hand corner. So if that's the case, then Li is going to come out to be perpendicular to both of these. And for these types of equations, for these types of problems, this isn't true in general, but in order to solve for it, be able to solve for it at the level that you're at right now, without having to deal with angular momentum matrices rather than just numbers, you're going to end up having a bunch of particles or a bunch of objects that are symmetric across the uh, z-axis. So if you have them symmetric across the z-axis, then all of the then all of these angular momentums, all of the uh, momenta, angular momenta vectors perpendicular to the x-axis or perpendicular to the z-axis is going to cancel out, so that when you add them up, it's just going to worry about the angular momentum in the z direction because everything in the xy plane is going to cancel out because these products or these materials that you're looking about are symmetric about the z-axis, which means that for every particle you have on one side of the xy plane, you're going to have another particle on the other side of the xy plane, uh, causing there to be a causing there to be a canceling out of uh, the xy components of angular momentum and only caring about the z components, which add up. So when you add them together, as you see on the bottom right-hand corner, uh, Li and Lj cancel each other out, and then oh, how did that happen? And then only the z component remains. So when we talk about when we talk about this now, we're going to only care about the z component. So going back to our demonstration up here, Li underscore z is going to be Li sine theta I, where theta is this angle that it r makes with the with the z axis rather, which is going to be ri times delta mi vi sine theta I equals ri sine theta I times delta mi times vi, which is going to be equal to big Ri times delta mi vi, where big Ri is just the projection of the r axis along the xy plane. So if that's the case, then we add up, in order to find the total angular momentum, we add up all of these LIZs, add up big Ri delta MIV, uh, add up big Ri delta M times big Ri times omega, because that's going to be our uh, angular velocity, no matter what velocity or no matter what radius you are, what you care about is how far perpendicular to the axis of rotation it is. So, uh, in order to find the velocity of the particle moving in a circle. So, if I'm going here, if I have this very slight angle and I'm going in a circle like this, then it's going to have a velocity equal to this this little distance from uh the tip of the pin to the z-axis times omega. But if I go farther out like this and rotate like this, then it's going to be this entire distance from the tip of the pin to the z-axis times omega to find the velocity. So Ri uh, delta mi times Ri omega is equal to omega times the sum of mi Ri squared, which is just I times omega. So uh, L is equal to R cross P is equal to I cross omega, and dl dp is equal to, or dl dt is equal to the torque total. So yeah, this is pretty analogous to what you've been doing before. It's just the same thing, but with uh your linear yeah, your linear variables swapped out with their angular analogs. So Uh, with that said, yeah, let's just do one quick drawing. So if you have a merry-go-round and somebody that's going with that has an initial total angular velocity L equals I omega naught, and then somebody jumps on the merry-go-round at a radius r from the center of mass, then they're by conservation of angular momentum, this is going to the new center, the new uh yeah, the new angular momentum is going to be equal to the old angular momentum. M d is equal to I plus m d squared omega nu. So omega nu is going to be I divided by I plus m d squared times the omega naught. So it's going to be somewhat smaller than the initial velocity. So basically what you're doing is you're by adding more mass at some distance far away from the at some distance away from the axis of rotation, you're changing the angular or not the angular momentum, the angular momentum stays constant. That's the exact reason that we did this problem. But you're changing the moment of inertia, which means that your new moment is going to it's going to be harder to spin because there's an extra mass and at an extra distance away. So it's going to have some angular velocity smaller than the initial angular velocity. And then another thing that I just want to bring up really quickly is the figure skater, who's able to so omega nu equals I naught over I nu omega naught, just to generalize this. So if you have a figure skater who's initially has their arms outstretched and is spinning around like that, then they have a high I naught. They have a high moment of inertia. But if they bring their arms in and bring them up to their chest, then they drastically lower the radius, the initial radius, uh, the initial radius of the particles in their body, and spin around a lot faster. So by uh, the conservation of angular momentum, you're able to spin around a lot faster if you scrunch up rather than if you let yourself starfish out. So that's because I knew is going to be bigger, or it's going to be a lot smaller than the I initial. So this omega nu is going to be a lot bigger than the omega initial. All right, so that's basically all I have to say about angular momentum. I'm going to do one more uh, lecture or one more section about torque and then leave you be. Awesome. Thank you very much.